The modern transportation system provides essential services for a nation's livelihood and economic prosperity. This system consists of streets, roads, highways, bridges, railways, pipelines, and terminals, such as airports, ports, and stations. The relationship between the transportation system and the environment it transects is symbiotic. How can we make responsible decisions to reduce negative impacts from the transportation system on the environment?
Environmental sustainability should be considered through the entire life cycle of the transportation system, from planning, design, material selection, construction, maintenance and operations, preservation, to recycling.
Innovations in material and design are being continuously developed by the transportation industry and its agency partners in order to improve infrastructure performance, increase construction efficiency, conserve resources, and seek greater environmental benefits. The use of warm mix asphalt, or WMA, in pavement construction is an example of sustainable innovation. Compared to traditional hot mix asphalt that generates emissions of volatile organic compounds during production and placement, WMA techniques can reduce the asphalt mixing and compaction temperatures by 30 to 70 degrees Fahrenheit, thus requiring less fuel for heating materials and reducing emissions at mix plants and fume exposure for workers at job sites. Various WMA technologies have been developed to reduce asphalt viscosity at lower temperature, including plant foaming by injecting water into the hot asphalt and adding organic additives such as sasabit, which are soluble in asphalt, or chemical agents like Evotherm to create a dispersed asphalt system. Numerous national and international studies and field practices have indicated that using WMA techniques improved workability and compaction, and extended pavement service life due to the asphalt binder being less age-hardened at lower temperature. Research is still underway to monitor WMA's long-term performance as well as its performance when combined with other sustainable technologies. Pervious concrete for sustainable stormwater management is an emerging technology. Pervious concrete is a high-porosity concrete that contains little or no sand. It allows much higher water flow rate than traditional impervious pavement surfaces. Dr. Hasselbach's work addresses several unknowns, such as pervious concrete's durability in wintertime and the impact of storing water for extended time on neighboring pavements or soils. Field test sections were built for this study in Pullman, Washington, and soil moisture and temperature probes were installed to collect data periodically. More promising research is being done in Dr. Jianming Shi's lab.
In my laboratory, we research fly ash concrete such as 100% fly ash pervious concrete.
Dr. Shi is using coal fly ash, a byproduct from coal combustion and treated with nanotechnology to replace Portland cement, so the environmental footprint of pervious concrete can be further reduced. Material innovations have also been developed to address issues encountered in transportation systems. For example, using paving interlayers to control the propagation of existing cracks and other road deteriorations. This also provides waterproofing control against infiltration of free surface water through the pavement into the base and subgrade soils. Dr. Ginny Liu's group further explored the effectiveness of several innovative paving interlayers through laboratory evaluation and computer-based simulation. They found those paving interlayers showed high strength and better bonding with the pavement. The reinforced asphalt mixtures demonstrated greatly reduced permeability and improved the capability of retarding existing cracks. With help from the Alaska Department of Transportation, Dr. Liu's group established field test sections and conducted continuous monitoring in recent years. Compared with the control section without any paving interlayer, reinforced pavements have all been observed to perform better in terms of crack amount and severity level. Frost heave and thaw weakening cause extensive damage to transportation infrastructure in cold areas, such as Alaska. The key to eliminate, or at least minimize this issue is to drive water out of soil. Dr. Zhang Zhang introduced one innovative wicking fabric to be placed in subsoil areas, which has unique hydrophilic and hygroscopic material that provides wicking action to effectively suck water away. In his work, wicking fabric field sections were built at many locations on the Dalton Highway, the famous North Slope Hall Road, in 2010, where soft spots had occurred most frequently in previous years. The use of this wicking fabric may result in estimated savings of $2.5 million from the initial construction costs. So far, no frost heave damage has been observed according to several years' field monitoring. Nearly 97% of unpaved roads are in rural America. When vehicles drive on the unpaved roads, they spin up microbial agents or dust, creating public health and safety issues. Pavement engineers recommend several approaches for dust control: reducing the driving speed, watering the road, spreading gravel, and using chemical dust suppressants. Dr. David Barnes at the University of Alaska Fairbanks is currently studying the proper application of synthetic fluid palliatives, which have proven effective for dust control, in order to create guidelines for field implementation. His group is seeking to establish two correlations. One is between the physical properties of aggregate and palliative performance, and the other is between a standard dustfall lab test and a field-based test. The field test is to be accomplished by a non-stationary dust monitoring system that is designed to be easily deployed in remote locations. The research outcomes will be used to develop engineering guidelines for road dust control using synthetic fluid palliatives. In wintertime, careful snow and ice control is a must-do task for highway personnel to make winter roads passable. Pre-wetting and spreading sand or abrasives to provide traction, applying de-icing chemical agents, and then physically removing snow or ice from the road and other surfaces are very common winter maintenance practices. A proactive approach is applying anti-icing agents, which not only de-ice, but remain on the road surface to delay the reformation of ice. Recently, Dr. Jianming Shi at Washington State University has successfully identified beet sugar refining byproducts as alternative anti-icing additives. Given that ice control chemicals are plagued by growing environmental concerns, using the green waste sugar beet anti-icing agent for winter snow and ice control has the potential to make our road system more organic. One issue associated with transportation systems is air quality. Dr. Agarwal at the University of Alaska Fairbanks has set up air quality data collecting stations at 5 key roadside locations in Fairbanks, Alaska.
The goal of this research is to explore the dependence of roadside air quality on traffic stream characteristics and meteorological conditions. So we are factoring in several potential variables like traffic speed, volume, composition, temperature, relative humidity, barometric pressure, and wind speed.
Drs. Tom Jobson and Serena Chung's work targets vehicle cold start and idling issues in wintertime. Low-lying temperature inversions can trap pollutants from cold starts and idling dangerously close to the surface. Their team used fast-response, high-accuracy instrumentation to measure emissions from 4 gasoline and diesel engines in Washington State University's Mobile Atmospheric Chemistry Lab. The data they collected were used to establish an accurate emissions inventory and to correct the established EPA model, which underestimated emissions of some air toxics in colder climates. In order to build transportation systems, forests and natural land must be converted, which may aggravate soil erosion when storms occur. Erosion of soil slopes can undermine pavements and create safety hazards. The Road Ecology Group at the Western Transportation Institute is exploring emerging techniques such as using wool byproducts for erosion control. Wool can store up to 400% of its weight in water, which has great potential to outperform the current standard practice of using a coconut straw blanket.
The nice thing is we will be using the wool that is not used for the manufacturing of clothing, but is actually left on the farm and ranches.
Up to 30 million pounds of this waste wool product can potentially be used in the United States as erosion control blankets, silt fences, and as a compost additive. The same group is also evaluating planting roadside vegetation common to northern states for soil retention, which carries the additional benefit of increasing carbon stores in roadside plants. Building and preserving transportation infrastructure affects ecosystems every day. It may cause wildlife habitat fragmentation, forcing wildlife to cross the infrastructure, thus leading to potential wildlife vehicle collisions. Wildlife crossing structures allow animals to cross highways safely, such as underpass tunnels, viaducts, and overpasses. To evaluate their effectiveness, researchers have used camera traps and infrared monitoring systems to monitor wildlife's use of established crossing structures. Another emerging and effective measure is using animal detection systems that alert motorists to animals crossing the road. Dr. Marcel Hauser is using meta-analyses to quantify the reliability and effectiveness of various animal detection systems. His study has a special focus on extreme conditions, such as low temperatures and snow and ice, which are harsh for electronic equipment and relatively dangerous for driving. We need structures such as dams, bridges, and culverts to cross and manage water, but these structures affect marine ecosystems as well. These structures may impede fish migratory passages, which can affect fish populations. In order to balance this need for fish passage, Montana State University researchers are seeking the most effective design and engineering practices for hydraulic structures. They are taking consideration of proper sizing, maintaining structures' flood resilience, water ecology, as well as operation and maintenance costs. When transportation infrastructure reaches retirement, recycling is a sustainable solution for the environment and communities. For example, small pieces of crushed recycled concrete can be used as aggregate for new construction projects, with large pieces used as sloping structures for stream bank erosion control. Promising products are recycled tires that can be used as lightweight fill for construction of road and retaining structures, or made into a crumb rubber additive for asphalt mixture. Recycled glass to partially replace raw aggregate in construction, gypsum, and gabions. The most recycled product in America is reclaimed asphalt pavement, or RAP. Incorporation of RAP into new asphalt mixture can reduce the amount of virgin asphalt binder and aggregate, thus conserving natural resources. The average estimated RAP used in all mixes has increased from 15.6% in 2009 to 20.4% in 2014, according to a national survey in the U.S. Some ongoing studies are dealing with issues due to age-hardened asphalt in RAP, such as a potential compromise of pavement's resistance to fatigue and low-temperature cracking, an unknown portion of RAP binder peeled off aggregate during mixing and available for reuse. It is important to quantify how transportation infrastructure will impact the environment. Life Cycle Assessment, LCA, is one of the most effective tools for this purpose. It includes a systematic consideration of environmental components, such as emissions of greenhouse gas and other standard pollutants. A number of programs have been developed to facilitate this process. Researchers at the Center for Environmentally Sustainable Transportation in Cold Climates, CESTIC, have also produced a transportation-focused LCA toolbox. They are currently developing case studies to link representative CESTIC projects with environmental assessment. Transportation infrastructure affects all of us, so getting research results out of the laboratory and field test sites and into the hands of the public where it can make the biggest impact is essential. CESTIC is taking the lead in technology transfer efforts through conferences, workshops, public presentations, trainings, and classes. The International Symposium on Systematic Approaches to Environmental Sustainability in Transportation in 2015 gathered over 100 professionals to Alaska to discuss challenges and showcase recent developments and advances in this field. SESTIC has collaborated with the Alaska Tribal Technical Assistance Program, the American Society of Civil Engineers, the Alaska Society of Professional Engineers, and other university transportation centers in a number of ways, and the monthly webinar series has been well received by transportation professionals. The center has presented at numerous STEM-focused programs and events, such as Kids to College, Imagine Tomorrow, and the Future Cities competition. SESTIC continues to promote the long-term goal of enhancing environmental sustainability concepts in modern transportation infrastructure. We hope the next generation of Americans will make wise lifestyle choices to substantially reduce their environmental footprint.